Chapter 4 is called The Generative Models of Active Inference, and it begins with a quotation, "Everything should be made as simple as possible, but not simpler," by Albert Einstein. Ali, what is your overview, thought, or warning for Chapter 4?
Okay, so after the preliminary materials in chapters 2 and 3, which was basically largely based on providing some conceptual framework for developing the further theory, Chapter 4 delves into much more detail in terms of mathematical formulation, and it unpacks a lot more the way that the central equations of active inference is derived, and how to construct the important elements of active inference models. So say matrices A, B, C, and D, and also how to put together generative models in different situations. So it basically lays out the foundation for constructing active inference models, both for discrete time situations and continuous time ones, which will be used later in chapters 7 and 8. But this is probably one of the most challenging and at least mathematically dense chapters in the book. So I would personally suggest reading through this chapter really slowly, and even if we don't get to understand every single detail of the chapter, obviously we can return per required as we go through the textbook.
Thank you, Ali. Yes. So let's look through the sections. Just to add on, though, Chapter 4 is one of the larger and more equation-dense chapters because it is the common kernel or basis that's then going to get applied in Chapter 5 in the neurobiological case. There's a recipe for making Chapter 4 in Chapter 6. That's the recipe for active inference modeling. Chapter 7 and 8 are about the discrete and the continuous time variant or subtype or motif of these kinds of things called generative models. So this is the real common root, and we'll just look at what the sections are. This chapter complements the preceding chapter's conceptual treatment of active inference with a more formal treatment. Section 4.2, from Bayesian inference to free energy. What would you say about this section, Ali?
Okay, so as we know, the free energy principle is inspired by previous work on Bayesian inference. All the way back to Helmholtz's theory about unconscious inference or something to that effect. I can't remember the exact term, but here, it provides in a bit more detail how we can derive free energy principle formalism using the established Bayesian inference formulation, and particularly one of the key movements, or at least one of the key decisions through the derivation of free energy principle formulation is using Jane's inequality principle to derive an upper bound instead of just using the exact values to compute or to achieve the required parameters. So that's basically, in my opinion, the key premise of section 4.2, and to see in a bit more detail how we can achieve those upper bounds using Jane's inequality directly by using manipulations of Bayesian inference, Bayesian statistical formalism.
Thanks. I'll just add one point from this section. Broadly, these are the problems of inferring states of the world, perception, and inferring a course of action planning. So this is again referring to the perception and action, and everything that happens in between is the internal or the cognitive part of the inference, but this is like the blanket state, cybernetic input output. And then let's look at the first equation, or how much equations overall, or what equations do you think we should highlight?
Uh, okay, so maybe we can, I mean, uh, just as a general comment about these different equations, well, each of these equations provide a distinct step toward deriving the ultimate whole picture. So even if we don't quite understand how we can derive from each step to the other one, it's good to know that it's only required to understand how we get to that ultimate whole picture. But ultimately, what we would need in order to develop develop active inference models is the ultimate equation or ultimate whole picture. So this is just a way to elucidate the steps toward developing that whole picture. But again, it's not an essential requirement to understand the materials of the rest of the book. But if we go from, equations 4.1 toward the 4.4, or other words, the free variational free energy, well, equation 4.1 is just a basic definition of some properties of probabilities in terms of conditional probability and so on. So equation 4.2 provides the central Jane's inequality principle and how it relates to conditional probabilities and, of course, joint probabilities. And then by using those two properties, or those two equations, we ultimately get to 4.4, which is the definition of variation-free energy parameter, which is the parameter of interest that needs to be optimized in order to inference to happen, or at least perceptual inference to happen in active inference models.
Thanks. Only thing I'll add is F is the letter used for variational free energy. You can think of it like a computer program, and the arguments that it takes in, or the variables that it takes in, are Q, which is the distribution that's under the statistician's control, and Y, which are the data which are outside of the statistician's control. And do you want to describe more about anything in this equation, or carry on?
Just one thing that can probably be helpful is to somehow compare these steps with the initial picture we had from chapter 2, because variation-free energy was first introduced in chapter 2. So it can be helpful to go back and forth between chapters 2 and 4 and try to connect the dots between the related points there.
Section 4.3, generative models. All right, I'll read the first sentence, then you can give some thoughts. To calculate the free energy, we need three things: data, a family of variational distributions, and a generative model comprising a prior and a likelihood. In this section, we outline two very general sorts of generative model used for active inference and the form the free energy takes in relation to each.
Okay, so as mentioned earlier, this chapter deals both with discrete time and continuous time situations. So clearly, we would need two different types of generative models for each situation. And obviously, the generative models or the way to construct generative models for discrete time situations would vary quite a bit from the one for continuous time situations. But the general principle underlying those generative models are basically the same, which is, to somehow construct a model of the environment. Either be it for the situation uh, that is sequential in time, or for the situations that need to be somehow each moment of the situation needs to be accommodated in terms of a continuous time situation. So figure 4.2 provides some examples of both. So yes, let me see. Yes, we have some examples of different kinds of generative models, some uh, case case studies, if you like, and it provides various ways to show how the dependencies between variables can be modeled using these kinds of graphical probabilistic models. So one common way to represent generative models is to use these kinds of graphical probabilistic models in active inference literature, which is, at least in this case, the circles would represent the random variables, and the squares would represent the distributions, which would describe the dependencies between those random variables. So we can see the clear relationships between those parameters here, which is basically what this whole graph, what constitutes the generative model that needs to be used for different situations. And then in figure 4.3, we can compare the two different types of generative models based on whether it's discrete time or continuous time situations. So the upper picture is a generative model for the discrete time situation, and the lower picture is the parallel continuous time version of it. And as we can see, the general topology of these models are the same. The only things that differ is the use of parameters for policies, or discrete time policies, or the continuous time ones. And we can obviously compare the different elements for both priors, states, and external states, internal states, and so on by comparing these two models here.
Yeah, we often return to figure 4.3. It's kind of the Rosetta Stone of generative modeling for the context of this book, because it's then going to develop out into chapter 7 and 8, and it represents a really fundamental decision made in modeling. And in the later chapters, it's also shown how it can be made into a hierarchical model that combines aspects of both. But within each level of modeling, still, these are the kinds of decisions that modelers are presented with when it comes to statistical modeling overall. So section 4.4 goes into essentially the top half of figure 4.3, discrete time. What would you say about discrete time?
Okay, so the discrete time situation is obviously the archetype discrete time situation, which is the POM-DP models. So at this point, I would very much like to recommend following the steps, following the material from step-by-step paper, because that's in that paper, the way to construct POMDP models is described in a bit more detail. So if anyone feels like they should learn a bit more about the gaps in the details, I would very much like to recommend that particular paper. So yeah, I don't know how much detail we should go into, because it's, I mean, although it's not maybe detailed enough for some tastes, but it goes in a quite extensive detail about how we can construct these models using the concepts we've learned in previous chapters. So ultimately, we reach equations 4.13 and 4.14, which are basically the culmination of POMDP formulation using the vector notations and gradients and so on. So
That's
yeah, and then
great.
we go to continuous time
Yeah,
situation.
great. A few things intervene in the continuous time chapter, ones that we'll just mention here because they're kind of boxed or partitioned from the continuous time part, but they're following pages. First is Markov blankets. We won't go into it here, but kind of footnote that or look at some other places where we talk about it outside of this chapter overview. Figure 4.4, Bayesian message passing. Again, a big topic. Let's kind of just go past it now. We're back to the regularly scheduled continuous time generative model discussion. And then another box to the generalized coordinates of motion. So taking position plus derivatives of position. And that has some beneficial properties that are described and unpacked also elsewhere. Do you want to say anything about 4.5.2?
Uh, well, the only thing that comes to mind is, although, as I said before, all the formulations here may look more, I mean, a bit too dense to understand at the first pass. But some of the key, maybe components here could be obviously the material from box 4.2 and 4.3 is. I think are quite essential to understand uh, the underlying principle behind deriving the continuous time situation, because without Laplace approximation, what we would have in terms of free energy minimization is it would look very much like the Gibbs free energy. So, I mean, the key distinction between the free energy principle as described in active inference literature, as opposed to Gibbs free energy, is this distinction, is the Laplace approximation. So this is what enables us to go from Gibbs free energy to, the variation of free energy. So yeah, that's, quite essential to make this to be familiar with this essential approximation, and obviously the concept of generalized coordinates of motion will come time and time again throughout the whole book, particularly in chapters 8 and 9. So yeah, those two concepts, I believe, needs a bit more attention. So
Yeah, sounds good. Box
yeah.
4.3, Laplace approximation, equations, another message passing representation, and a summary. The key message to take away is that approximate Bayesian inference may be framed as minimizing a quantity known as variational free energy. This depends on a generative model that expresses our belief about how data are generated. Anything else you want to add?
Nothing comes to mind at the moment because, uh, as I said, this is, I mean, we're still in the stage that we want to develop our essential tools to be used in the rest of the book. So, here, up until now, I believe, by the end of chapter 4, we have acquired all the essential necessary mathematical tools. And the next chapter, chapter 5, is kind of acts like an interlude. Uh, and I don't think it's the direct, I mean, continuation of chapters 1 through 4. So I believe the first section or the first part of the book uh, conceptually and mathematically ends here. So yeah, that's it.
Yes, it's a little bit like the pragmatic modeling part gets foreshadowed or explored in 5, now that we're all built up with 4. All right, that's the end of the overview for 4.